Hey everyone, I'm Alexandre Honorat, a PhD student of INSA Rennes in France, supervised by Carole Desnos and Jean-François Desans. I will present the paper entitled Scheduling of Synchronous Data Flow Graphs with Partially Periodic Real-Time Constraints. This work has been done in collaboration with Shubhra Bhattacharya, who is professor at the University of Maryland and holds an international chair at INSA Rennes. This work has been partly funded by the European Union by the Cerbero project. So first of all, why do we use the synchronous data flow model? It is a common model to describe signal and image processing applications. The LabVIEW software, for example, supports a similar model. In our team, we are especially interested by image processing applications, which are modeled using SDF. In such applications, we often have real-time constraints, at least for the camera and for the screen, but generally not for the processing in between. Thus, we would like to combine the SDF model with real-time constraints, but only on specific elements of the application, as the camera captor. Hence, we speak in this paper about partially real-time constraints. Okay, now what is our goal? First, we would like to express the partially real-time constraints on an SDF application and know if a schedule might exist. Our contribution on this point is a necessary condition. Second, we would like to actually compute this schedule quickly if possible. We have developed an heuristic for this purpose. And third, we want to evaluate our necessary condition and scheduling heuristics. Before presenting these 3 points, let me start with some context on the SDF model and partially real-time constraints. The SDF model is expressed by a specific diacritic graph representing processing actors as nodes, exchanging data through buffers as edges. Such SDF graphs also holds the amount of data exchange represented by numbers on the 2 extremities of each buffer. In the sample graph below, the actor A produces 5 data units each time it is fired. The data are available at the end of the actor firing. These 5 data units are stored in the buffer in a first-in, first-out queue. On the right side of the graph, actor B consumes 3 data units at each firing. The SDF model also defines a vector called repetition vector. This vector states how many times each actor of the graph must be executed, so that all produced data are consumed. In the SDF graph below, the repetition vector states 3 firings of A for 5 firings of B. 3 times 5 is equal to 5 times 3, so all data produced by A are well consumed by B. For simplicity, we will use the same sample graph during the whole presentation. Thanks to the repetition vector, it is possible to compute a schedule, as shown here. The same schedule is usually repeated indefinitely. Okay, that's it for the SDF model. Now the partially real-time constraints. Such constraints applied on SDF actually are a submodel of polygraph. If an SDF actor is described as periodic, its multiple firings follow the standard periodic model of Liu and Leyland. Each periodic firing is made available every t time unit, t being the period. The hard deadline is also of period t. The periodic actors are a subset of all actors of the SDF graph, denoted P with calligraphic style. Let's see an example. We always use the same SDF graph, and now actor A is periodic. Its period is equal to 5 time units. On the SDF graph, there is a dotted blue pattern on actor A to represent its periodic behavior. And on the schedule just below, the orange down arrows represent the periodic deadlines of A. One scheduler iteration is represented. I will now talk about the first contribution, a necessary condition on the scheduling of SDF graphs with partially periodic constraints. Let's start with the most well-known necessary condition, the one derived from the processor utilization factor. We will reformulate the processor utilization factor U in our context. First, we notice that all number of firings are linearly related. Equation 2 derives directly from the definition of the repetition vector. I will not explain all the formula shown in this slide, but just give you the hints about how we obtain them. As all number of firings are linearly related, there is a unique graph period. This is equation 3. This graph period will be the duration of any scheduler iteration. Note that we can also define a scheduler iteration duration, that is a graph period, without having any periodic actor in the graph. Finally, thanks to this graph period, we can rewrite the processor utilization factor U as the sum of the periodic actor utilization factor plus all non-periodic actors over the graph period. It is the equation 4. Equation 4 is a necessary condition. It means that if the number of homogeneous scores M is lower than U, then there is no possible valid schedule. Otherwise, there might be a valid schedule. However, the processor utilization factor is a simple but imprecise test. We would like to do better. For this purpose, we will introduce a common assumption, which is there are as many firings per scheduler iteration as stated by the repetition vector. Here is a counter example. The first 5 firings of B have been scheduled in the second scheduler iteration. And now this is a valid example, respecting our assumption. This assumption implies another simple necessary condition, which is our first contribution. I will only give you the intuition. We will check the dependencies of the last firing of any periodic actor. Why the last firing? Because for this one, we exactly know how many time remains to execute its outgoing dependencies. On this example, let's consider that the period of A is 3 time unit. If so, we cannot execute the 4th and 5th firing of B, which depend on the last firing of the periodic actor A. While the processor utilization factor does not detect a problem on this example, our necessary condition does. Note that symmetrically, this works also for the first firing of any periodic actor and its ongoing dependencies. I will not enter into the details of these necessary conditions, this would be too technical, and we have seen enough formula for today. So instead, let me speak about our second contribution, a scheduling heuristic, still for SDF graphs with partially periodic constraints. Concretely, what does our scheduler compute? For sure, we want to respect the partially periodic real-time constraints. Then we want to integrate our scheduler in an existing framework which has the following restrictions. Assumption 1 that we have previously seen, and non-preemptive scheduling. You might think that the absence of preemption is a major drawback, but we will see that it is not the case when there is a small number of periodic actors. Regarding the input, we require the partially periodic constraints, a directed acyclic graph of firings, deduced from the SDF graph of the application, the number of homogeneous scores, and finally the worst case execution time of each actor. Let's see now an example of SDF graph to directed acyclic graph transformation. This is done easily with linear complexity in the number of edges in the DAG. The DAG on the right will be the input of our scheduler. However, we need to reattach the partially constraints. We know a start time interval for each firing of a periodic actor. It is computing from equation 1. As all firings must end before the graph period, we can also compute a start time interval for all actors, thanks to a breadth first search graph traversal. The bounds of start time intervals correspond to as soon as possible and as late as possible scheduling, without resource constraints. From the first periodic firing A1, we know the start time interval of its two outgoing dependencies, B1 and B2. Now we do the same for A2, and the start time interval of B2 is updated since A2 will force B2 to start later. And the same for A3 and B4. Now we can perform a second traversal in the other direction, and start time of aperiodic firing may shrink the start time of periodic nodes, like for A3. Indeed, if B4 and B5 start as late as possible at time 14, A3 must end before 14, so A3 must start at maximum at 11 time unit. These start time annotations are crucial for our scheduler. We will use the average start time as sorting criterion of the ready firings. Indeed, our heuristic is quite similar to list scheduling, where firings are sorted by increasing average start time. Moreover, our heuristic is greedy and tries to fill the idle time with tasks which are ready earlier, thus breaking sometimes the order of the list. Finally, we perform mapping at the same time as scheduling, on a first-fit manner. If it is not possible to schedule the next firing in the list, the scheduler stops. Thus, our heuristic does not find a schedule in every case. Sometimes we have to retry with a higher number of available cores. We will now look at the performance of our scheduler and also our necessary condition. We performed 2 experiments to evaluate our contribution. The first experiment is run on 10 randomly generated SDF graphs. These graphs are generated by the turbine tool. Half of them are small with only 10 actors, while in the other half, each graph contains 100 actors. The worst case execution time of each actor is also randomly generated. Finally, we set 1 or 2 periodic actors with the smallest possible period. The smallest possible period is obtained manually and iteratively. It is the smallest period such that the minimum start time of any firing is still lower than its maximum start time. Otherwise, the graph would not be schedulable. The periodic actors are selected in the middle of the graph with a high number of firings so that we expect a strongly constrained system. We have implemented our contributions in the Prism open source framework. Prism is a research tool dedicated to the synthesis of SDF applications on embedded platforms. We have also implemented an optimal integer linear programming model of our scheduling problem, with a timeout of 12 hours. In this experiment, we test the schedulability on an increasing number of cores until a valid schedule is found. That way, our scheduler finds an upper bound of the number of cores required to execute an application. Here are the results for the small graphs. Utilization factor is the first column on the left, then follows our necessary condition, our scheduler, and on the right, the optimal solution. The number in ordinate is the smallest number of cores required according to the different algorithms. On each graph, 1 periodic actor is set. The first remark is that our schedule is close to the optimal. Third and fourth columns have at most 1 core of difference. Moreover, for the first graph and the fourth one, the optimal solver actually times out. Its formulation is indeed quadratic in the number of actors, itself multiplied by the number of cores. Even with multiple optimizations, as symmetry breaking and transitive closure, 12 hours is not always sufficient for 10 actors. At the opposite, our scheduler takes only a few milliseconds. Another remark is that our necessary condition is quite useless. It is better than the processor utilization factor only for the first graph. On the first graph, the processor utilization factor is close to 2, while the necessary condition gives 6 cores, which is still far less than the valid schedule requiring 10 cores. In the other cases, our necessary condition is equal to the sale value of the processor utilization factor. In all cases, the processor utilization factor is quite low compared to the number of cores required for the schedule. It confirms that our problem is heavily constrained. On large graphs, having 2 periodic actors among 100 actors, the conclusions are similar. However, on these graphs, we could not run the optimal solver in a reasonable time. At the opposite, our scheduler is scalable and takes in this case around 100 milliseconds. The necessary condition is still useless except for the 6th graph. Further investigations are needed to understand the characteristics of graph 1 and 6, where the necessary condition is slightly useful. Now you may wonder how our scheduler would behave against preemptive scheduling. We will test that in the following experiment. In this experiment, we use the beamformer application from the Streamit benchmark. Beamformer is a parallel application where each actor is fired only once. Then, optimal periods are computed by the ADFG tool under a global earliest deadline first policy. In this case, each actor is periodic, and preemption is allowed. Most probably, without preemption, setting all actors periodic would be inefficient. But we will see how our scheduler behaves if we set only a graph period, still without preemption. The goal is to obtain the smallest graph period, while the number of cores is increasing. If you remember, our scheduler is greedy. So if only a graph period is set and no actor period, the computed schedule is similar to as soon as possible schedule. Then we can refine an initial pessimistic graph period, which is by default the sum of execution times. The new graph period is the time unit of the last firing, in this example, 7. To compare the results of ADFG and our scheduler, we compare the graph period computed by ADFG and preemption with the graph period computed by our scheduler, so without preemption but after refinement. In this diagram, the graph period is inordinate and number of cores in abscissa. The green curve corresponds to the graph period obtained by our scheduler. It is slightly above the violet curve of ADFG. For sure, we cannot beat the graph period achieved with the global EDF policy, which is optimal. However, we are very close to it. It is not possible to distinguish the curve for small and high numbers of cores. Our conclusion is that when the real-time constraints are on the graph itself, or only on one actor, there is almost no performance loss with no preemptive scheduling. Indeed, in the case of ADFG, the performance comes from the pipelining of the application, which corresponds to add initial data in the buffers. To be fair, we use in our scheduler the same amount of initial data as computed by ADFG. It is now the time to conclude this presentation. In this presentation, we have tackled the scheduling of synchronous data flow graphs with partially periodic real-time constraints. We have made two contributions, a schedulability necessary condition and a fast scheduler. We have evaluated both, and we have compared them with optimal solutions. The scheduler is simple but quite promising, even if non-preemptive. Our future work mainly concerns the scheduler. We would like to update it to take into account heterogeneous cores. A long-term work would be to also take into account the communication time between the cores, especially if heterogeneous. So, thank you for watching this presentation, and don't hesitate to have a look at our Prism open source tool. You have the address in this slide. If you want any additional information, you can email me at alexandre.honorat@insa-ren.fr. Goodbye.